Okay, so what we're doing here is I'm going to be going over the functions and inverses, or inverses and logarithms page to start off, which starts with problem 13. Really the easiest thing to do is just to kind of explain the things that you have going on here. 13a gives you two tables and asks if one is a function of the other. Now, here's the thing. There's a tell you should go with. If I'm looking at a table of x and y values, if two things are functions, and I have an XY table for one and an XY table for another, what it should mean is that if I have something here that works, and this is my original function, if I have something here like, let's say, 3, 1, if this is an inverse, the whole purpose of these is that they're supposed to undo each other. So that would mean that if the inverse, if I had a 1, it would be reversed as a 3. It essentially takes every xy and flips it to a yx. A really good place to start to check for something like this, like with problem 13, is to see, do you have anything on the left-hand side that works with the right-hand side? And so as I look here, I'm looking at the right one with g of x. You better be looking at this at the same time because I can't write them, and this will take too long. The right-hand one with g of x, there's a bunch of fractions. The left-hand one has all whole numbers. So there could be something, but we've got to be sure. So what I'm going to do is take all of the whole number ones from g of x, which is this one, and that's -2, 0, and that is 1, 1, and it's 4, 2. Those are our whole numbers. I want to look at my f of x, the one over here, and see if those are flipped. So this is -2, 0. When I find 0 on this side, I get -2, so that one's a check. When I find 1 over here, it goes to 1, good. When I find 2 over here, it goes to 4, good. So all of these are reversed. That gives me a way for me to sort of think about what this problem is going to be. Now, the problem is I don't have enough to say consistently that's all of them. If you're in a hurry for your final and you just give an answer, you can say these values are reversed. That's enough to give me an indication that it is probably an inverse and you can go. What you really should do, though, if you look at the f of x, you've got a list of things there and you should be able to figure out what that function actually is. So as I'm looking here, the place I always start with is the 0, right? And I see what's going to be happening. So as this goes up 1, this goes up 3 here, 3 here, and if I look consistently, it goes up 3 every time. So what that means, if I'm going to be coming up with what the actual equation is, it would be helpful because then I can test what the inverse is. So the equation here, if it goes up by 3 every time, that means I'm going to have a 3 times x with whatever it is. And I always look at the 0 because that tells me where I start. 0, -2, so 3x minus 2 is a place I would look. Let's see if that works for the values I have here. Plugging in a 1, 3 times 1 is 3, minus 2 gives you 1. Good. Plugging in a 2, 3 times 2 is 6, minus 2 is 4. Good. And actually, I'll just take 5, 13 to see if that's also one that works. 3 times 5 is 15, minus 2 is 13. We're good. This is our f of x. Now, to be safe, to see if the other ones make some sense, then I'm going to find out what the inverse of this is. So we've done this a lot. There's going to be some problems later on the sheet we do. So we flip our x and our y. And I'm solving for it now, so I'm just going to move this stuff over. This will be x plus 2 is equal to 3y. Y equals x plus 2 over 3. Okay, so this is our inverse. This would be, if we're testing it, this will be our g of x. Now, what I'm going to do is just look at the sheet that I have here. I know my whole numbers work. Let's just plug in a couple of the numbers that are fractionals to see. If I plug in a -1 for the x, let's see what happens. Plugging in -1, we will get -1 plus 2 over 3. That is going to be a 1/3. So 1 goes to 1/3. So far, so good. I'll do this with 0, 2, just as a double check, and we should be in pretty good shape. 0 plus 2 over 3 is equal to 2/3. So 0 goes to 2/3. My friend, we are in business. So as we look at something like this, that allows us to figure out if we are looking at two inverses, and for 13a, yes, they are inverses. Now, when we look at 13b, this invokes the idea of how do we look at something graphically. But we need to remember, if things are graphically inverses, it would mean if I drew a line directly up the diagonal where y is equal to x, then whatever's over here is reflected over here. Now, this example that we have here is pretty cut and dry. We've got this here, we've got this here. Yeah, I would say just looking at it with the general sketch, we're looking at an absolute inverse. You can check some points, But really what you're looking at is to see, can you pick some points on this one that are x, y, that I find corresponding points over here that kind of function as the same y, x. And in the case of this, we really do find that. So it's a place of sort of seeing that out. But generally, if they have a reflection over that axis in the same way, we're in pretty good shape. When we actually get to the work portion of something like this, I'm going to go through and do problems 14a and d to show you sort of the things that you're going to do. But this is kind of a reinvention, not a reinvention, but sort of a repetition of the things that we just did in the last problem here. So this original function is y is equal to 3 times the quantity x plus 2 squared minus 1 over 4. And we're going to find the inverse. Now, you know, that doesn't seem fun, but, you know, neither does slapping yourself in the face. And gosh, we all know how much fun that is. So if I'm going to change this up, again, we trade the x and the y first. And I got to get to it. So I'm just going to keep peeling stuff off one piece at a time. Taking this 4, move it over to the other side by multiplying it. So we'll get 4x plus 3 times y plus 2 squared minus 1. Bring the 1 over, so we have 4x plus 1. It's 3 times y plus 2 squared. I'm going to divide by 3, so 4x plus 1 over 3 equals y plus 2 squared. If I got to get rid of that square root, or squared, I'm going to do a square root. This is ugly, but I don't care. Square root of this side equals y plus 2. It's very possible that your teacher will say that they don't want to have a square root underneath the bottom, but you know what? For the sake of just doing this, you're getting the right answer, and it really doesn't matter since you could use calculators to evaluate this. I would leave it this way. I'm going to move the 2 over to get to our y, so y is equal to square root of 4x plus 1 over 3 minus 2. That is our inverse, and that's legit. Now, I know when I've said before, when we solve these things, if you take a square root of both sides, you're supposed to include plus or minus, and you are. You absolutely are. But what happens here, when we take a look at this, because we're trying to find a function, what we have to recall is we can't have two answers for anything that we come in here. So when I take a square root and I'm dealing with finding an inverse function, we're just going to have to leave it this way. Now, if you feel compelled to include a plus and minus in front of there, I don't think that you're going to be wrong in terms of finding what it looks like. It just isn't going to be a function that way. So I would leave it this way. And you know, if you get that off on the final, you know, I'll argue your point for you as you go through that. Now, as we get to 14, all of the other ones are kind of similar, but I do want to look at one that's exponential that we have to use a logarithm to work with. So I'm going to take this off, and I'm going to change this to D now. And this is going to be, I think, if you didn't understand logs, but I know you do, this would be terribly painful, but I think we're going to be okay. Again, set it up, flip them. 2y plus 1 minus 5. Now again, when we're working with this, if you have an exponential like this, and we're going to be using logarithms, oh, look at that. Look at the lack of focus. Isn't that fun? I'm sure it will come back. There it comes. Okay, if we're trying to find our exponential, and we're trying to get to an exponent, I can't do it in the format that I have here. I have to isolate the exponential here so that it's just going to be a base, an exponent, and an answer over on this side. So I'm going to bring the 5 over first. We will have x plus 5 is equal to 4 raised to the quantity 2y plus 1. Now, because of the way that we had remembered this before when we go to logarithms, it was base, answer, exponent. I can put this in logarithmic form, but it has to be in that format. This is my answer, this is my base, this is my exponent. So I'm going to rewrite this as log base 4 of x plus 5 is equal to the exponent, which is 2y plus 1. It's the same general idea in terms of what happens, but as I look at something like this, if I rewrite it that way and I had it in this format, it makes it much cleaner, because now when I solve for y, I'm just kind of treating this as its own entity. So I'm going to take this 1, bring it over to the other side. We will have, but just to be safe, I'll show you what I'm going to do. I'm going to put the -1 plus log base 4 of x plus 5. And the reason I'm going to do that is because if I include this -1 afterwards, sometimes there's a confusion as to where stuff is coming from. And so I just want to make sure that we can take care of it that way. Now I'm going to divide by 2. So I'm going to divide these each individually. We will have -1/2 plus log base 4 of x plus 5 over 2 is equal to y. That, my friend, is our inverse of this problem. So we should be in pretty good shape with that. That is the way that we would end. That is our inverse, and that should be fine. I do want us to get to what we're supposed to do with problem 15, because it's asking you to do some investigations and talk about some different things. So they want you to investigate the function along with its inverse using multiple representations. So they want equation, a graph, a table, including important features, explain any similarities and differences between the two. Okay, so here's the way that I would approach a problem like 15, which I think is a very good one. Let's start off with just what it is. We got y is equal to the quantity x plus 3 squared minus 5. Now, what I'm going to tell you I think would be good before I do anything is to say, gosh, this is wonderful with my focus here. Gives me something to complain about, though, and you know how much I like that. I would actually say, write a couple things about this function first. We know it is a parabola. We know it has got a vertex of -3, -5. And, because it's here, I'm just going to graph it. And your graph will be much more complete than mine, but let's just do that anyways. So we're talking about this. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This is probably not enough. But if it's got a vertex of -3, -5, that means it moved to the left 3, and it moved down 5, so that's going to be our vertex. And I'm just going to graph the points that I have here. So we know that the parent graph of a parabola, over 1, up 1 on each side, and over 2, up 4 on each side. And I'm going to leave it at that. I know I could probably get up to the 9, but this is just to give me a general shape. So there's our graph, there's this, and it talks about finding the table as well. Well, okay. Here's what I would do. Because I've actually graphed this, what I would do is start with your point -3, knowing that you get at a -5. That's our vertex. Now, for the sake of doing the rest of it, I'm going to do some of the points to the left and the right. So we're going to go -2. When I plug in -2 to this, I'm going to be getting out a -4. You can meet this out by actually plugging this stuff in, but it's totally up to you. If I plug in a -1, I'm going to get out a -1. If I plug in a -4, I'm going to get out a -4. And if I plug in a -5, I'm going to get out a -1. The reason why I'm plugging them this way is I'm just basically keeping track of some points that I got when I did this graph. Now, I'm going to find the inverse, and we'll talk about sort of what we can do with the parts that we know of the inverse. If I'm going to do this as an inverse, let's do some trading. In this case, we're going to have x is equal to the quantity y plus 3 squared minus 5. Bring that 5 over here. X plus 5 is equal to y plus 3 squared. And because they want you to investigate the inverse, I know I have to take the square root. So what I'm going to do, I'm going to do the square root of x plus 5. That's totally fine. I'm going to put a little parentheses for you to remember a plus and minus, but I wouldn't worry about it yet. So it'll be y plus 3. And then I'm going to move this over here and say that y is equal to the square root of x plus 5 minus 3. Now, we did a parent function thing about square roots a little bit earlier. And again, I forgot to put my little in parentheses plus and minus. What we need to remember then is we know the parent function of this is a square root. I can tell you that its start, we're not going to call it the vertex because it's not exactly the same thing, but its start is at -5, -3. Okay, so we've got that in here. And what I need to do then is to do that graph. In the case of something like this, it shouldn't be too terribly bad for how I'm going to be doing that, but let's make something like that work. If the starting point is going to be at -5, -3, there we are. Now, I'm going to start graphing the points that I had for something like this. And what I'm going to do, just so we can see it a little bit better, is to say, if this is my starting point, and I know that as I look at something like this, it's going to be a parabola, or excuse me, the square root function, I know it's going to look like this. So I at least feel like I'm in decent shape, because that means as we went over 1, we'd go up 1. As I go over 4, I would go up 2. Well, that's actually the same point. And as I went over 9, that would be 5, 6, 7, 8, 9, I would go up 3. So it's like this. So as we look at this, I want to write those points down because this looks weird to me. This kind of feels like something is wrong. But let's just make sure. So I'm going to put my x and my y points for my square root. We'll start with this. We know we have a -5, -3 as our starting point. And what I really want to do is just look at each of the other points. The next point that I had was this one, which is -4, -2. The next one that I had was -1, -1. And then I had 4, 0, which I'm going to put over here because we actually don't have a pair. We don't have a pair up on the top here. So we know there's a 4, 0. Are each of these represented up here as a flipped point for our inverse? And the answer is absolutely. So we are really looking at an inverse. This is the functional approach of it. Because right now I had included the plus or minus here, if I want to graph what the inverse would look like, I could graph it, but from this point on, if I do these, we are no longer looking at a function. And I'll show you why. Because if we think about what would happen for plus or minus, that means then that if I was to plug in a -4, the other value that I could get would be down here at -4, -4. And while we have a pair for that up here, the problem is that we recognize that I now am not dealing with a function because I have 2 y values for an x value. I'm going to graph them anyways just for the sake of looking at it. The other one would be if I have a -1, I could also go to a -5. So that would give me a shape like this. Again, this meets out right up here. We have the exact same point we have there and there. It's just that we're not dealing with a function. But it'll work. I could feasibly draw a line through here. We have the reflection. We're in pretty good shape. But this is another piece of information that's there. Explain any similarities and differences between the two. Well, I think that, and I'm not writing these in words because it would be a pain to see, the similarities is the shape of the graphs are the same. It's just that one has been reflected over the line y is equal to x. We can say that the inverse, in order to stay an inverse, can only use half of the graph, whereas our original parent graph, our original function, can have the whole thing as a parabola. I think we can say that if we look at what has ended up happening here, one's a square root and one is a squared, so those things are inverses of each other both algebraically and graphically. I think we could say that our start points, whether it be a vertex or just a regular start point, are the flipped x and the y for what we have. I think we've got a lot of information to say about this. And all of the important features I think we have represented here. So this gives us a good idea as to what we are looking at. And that is the end of the page of inverses and logarithms, at least the first page.